For a $1 per square foot of aluminum foil reflective barrier, your attic stops being a furnace and starts being a thermal shield. And for 6 decades, the insulation industry spent millions of dollars making sure you never found out. In 1955, a NASA engineer named Clark E. Beck, working out of Wright-Patterson Air Force Base in Dayton, Ohio, developed a thin, reflective aluminum material capable of blocking more than 95% of radiant heat. The problem he was solving had nothing to do with your home. NASA needed to protect astronauts from temperature swings between -459 and +455 degrees Fahrenheit during spacewalks. Traditional insulation would have required a 7-foot-thick layer on every spacesuit. Instead, Beck's material, a few thousandths of an inch of aluminized film, did the job with essentially zero weight. The Gemini missions used it. The Apollo missions used it. Every crewed NASA spacecraft since has used it. In 1996, the Space Foundation inducted the technology into its Space Technology Hall of Fame. In 2013, NASA's own spin-off publication confirmed that nearly half of all spin-off issues since 1976 featured products built on this same radiant barrier principle. The global residential insulation market is valued at over $40 billion annually. Fiberglass, cellulose, and spray foam account for the vast majority of that figure. These materials are manufactured, branded, sold in bulk to contractors, and installed at rates ranging from $1 to $5 per square foot in labor. A roll of double-sided radiant barrier foil costs between 20 and 90 cents per square foot in materials. A standard 1,200 square foot attic can be covered for under $200 in product. The labor, if you do it yourself, is a weekend and a staple gun. There is no license to renew, no proprietary formula to patent, no brand to grow. That combination, cheap, unpatentable, and highly effective, is precisely why the traditional insulation industry spent decades and millions of marketing dollars redirecting consumer attention toward R-value ratings, a measurement system that radiant barriers do not use because they work on entirely different physics. The concept predates NASA by a century. In the early 1800s, the French physicist Jean-Claude Eugène Peclet demonstrated that mirror-coated steel plates arranged with air gaps could provide insulation equivalent to 3 inches of cork. The underlying physics were established long before the materials were practical. By 1925, 2 German engineers named Schmidt and Dykerhoff had filed patents on reflective surfaces for building insulation. In the 1940s, Alexander Schwartz commercialized the idea through a company called Infra Insulation Inc. in New York City, producing reflective foil products that architects and builders adopted rapidly. Millions of square feet were installed across the United States by the early 1960s. In Japan, reflective building materials have been used routinely in residential and commercial construction since the post-war housing boom of the 1950s, where summer heat management is treated as a structural engineering problem, not an aftermarket fix. In ancient Rome, engineers building in North Africa and the Levant used double-wall construction with air gaps specifically to exploit the same physics, reducing the radiant load on interior surfaces by interrupting direct heat transfer paths. The physics did not change, only the materials evolved. In 1968, NASA's Marshall Space Flight Center contracted the Metallized Products Division of National Research Corporation to produce a layered super insulation called NRC-2, built from crinkled aluminized mylar. This material became the template for what NASA describes as modern radiant barrier technology in its published spin-off documentation. The technology was released into the public domain. By 1991, the U.S. Department of Energy had funded multiple field studies in Florida, Texas, and the Gulf Coast examining the cooling cost impact of radiant barriers installed in residential attics. Those studies confirmed cooling cost reductions of 5 to 12% in warm and sunny climates. The fiberglass lobby responded not with technical rebuttal, but with a sustained campaign to educate consumers and building code officials about R-value as the primary metric of insulation performance. A metric that, by definition, does not apply to barriers that work through reflection rather than absorption. By the mid-1990s, the R-value framework was embedded in most state building codes. Radiant barriers nearly disappeared from mainstream contractor recommendations in northern and midwestern markets, surviving primarily in Florida, Texas, Arizona, and other states where summer cooling costs are impossible to ignore. In the description, you'll find a complete guide with the installation methods, material specs, and sourcing details that energy-efficient builders use routinely and that most HVAC contractors never mention. Here's what the installation actually looks like. You buy double-sided perforated radiant barrier foil from any major home improvement retailer or online supplier. Brands like Radiant Guard, Attic Foil, and Reflectix are widely available. A 500 square foot roll costs between $50 and $90 at retail, the equivalent of roughly 10 to 15 cents per square foot of coverage. You need a staple gun loaded with half-inch T50 staples, a utility knife, aluminum HVAC tape, and a roll of measuring tape. The installation method with the highest thermal performance is stapling the foil directly to the underside of your roof rafters, reflective face toward the attic space below, allowing a minimum 1-inch air gap between the foil and the roof sheathing above. The air gap is not optional. Without it, the barrier cannot reflect. It conducts instead. Work from the ridge toward the eaves, cutting panels between rafters and stapling every 12 inches. Leave the soffit and ridge vents unblocked. Tape all seams with aluminum foil HVAC tape. Do not lay the foil flat on top of your existing attic insulation. Dust accumulation reduces reflectivity over time, and moisture can become trapped beneath the foil. The staple-up rafter method avoids both problems. For a 1,200 square foot attic, the material cost runs between $140 and $220. A professional contractor charges between $700 and $2,800 to do the same job, depending on access and local labor rates. The DIY installation takes 1 full day for a person working alone in a standard vented attic. The payback period in a hot climate, Florida, Texas, the Gulf Coast, the Southwest, is typically less than 3 cooling seasons. In climates with long, intense summers and high electricity costs, homeowners have documented reductions in monthly summer bills ranging from 15 to 27% when radiant barrier installation was combined with adequate attic ventilation and existing conventional insulation. The physics that Beck applied in 1955 at Wright-Patterson Air Force Base were the same physics that Peclet described in the 1800s, that Schmidt and Dykerhoff patented in the 1920s, that Schwartz commercialized in New York in the 1940s, that Japanese builders integrated into post-war residential construction, and that Roman engineers exploited through double-wall design 2,000 years before aluminum film existed. The only thing that changed between then and now was the creation of a marketing framework specifically designed to make you forget about all of it. A roll of reflective foil costs under $100. A staple gun costs $15. The science is not complicated. The savings are real. If this video gave you something useful, share it with whoever is paying too much to cool a house that has an attic full of untapped potential. And subscribe so you see the next one before the algorithm buries it.